Hi, this is a video to help you through the activity on attractive forces and physical properties. Please take a look at the table on the first page of your activity. I'd like you to notice that attractive forces are listed in the right-hand column here. These are the attractive forces in their respective substances, which are listed here. In this column, you have the substance name and its condensed structural formula. And in this column, you have a representation for its structure. We've also listed the boiling points and the melting points. In the first three cases, the boiling point is not listed because it's too high to be measured. The substances here are listed from the strongest forces to the weakest forces. Ionic attractions are the strongest forces between two molecules or ions, and London forces are the weakest attractions between molecules. I'd like you to take a moment to look at this table and to read over the material in the first 2 pages. Room temperature is usually accepted to be close to 20 degrees Celsius, or in a range between 68 and 72 degrees Fahrenheit. I'd like to mark where room temperature falls in the boiling and condensing column and the melting and freezing column. 20 degrees Celsius is room temperature. So it would be right around here in this column or right around here in this column. I'd like you to mark those things. Now let's talk about water. Room temperature is between the boiling point and the melting point of water. So 20 degrees Celsius room temperature is between the boiling point and the melting point, 100 and 0. For this reason, we know water as liquid at room temperature. Let's look at this in a different way. Here are 2 scales, the Fahrenheit and the Celsius, represented on figures of a thermometer. I've labeled room temperature here. I'm going to call room temperature 68 Fahrenheit or 20 Celsius. Here's room temperature. The boiling point of water is much higher on this scale, and the freezing point of water is much lower on the scale. Between the freezing and boiling point of any substance, you will see the substance as a liquid. And that's why at 20 degrees Celsius, when we're between the temperature for the boiling and freezing points, we know water as a liquid. When molecules are in a liquid form, they are interacting with each other. Here's a cartoon to represent this. This is a cartoon where I'm representing molecules as little spheres or little green balls here. And if I could animate my slide, I would show that these little balls are moving all around. So they're touching each other, but they aren't fixed to one another. They can move. If I would heat up the water, so if I started at 20 degrees and I heated the temperature up to this point here, this is the boiling and condensing point of water. This is when the liquid water would begin to boil and it would turn into a vapor. When a substance goes from a liquid phase to a gas phase, the molecules separate completely. In the gas phase, the molecules are not touching each other. And so attractive forces that are present in the liquid have to be broken to form a gas. At any temperature that is above the boiling point of a substance, that substance will exist as a gas. In the case of water, if you heat water to above 100 degrees Celsius, it will exist as a gas or water vapor. On the other hand, if you cool the temperature of a room down to below freezing, or if you just walk outside in the winter, you'll do this. When you cool the temperature down to below the freezing point, the liquid starts becoming fixed. The little molecules interact with each other really strongly and they form a crystal structure. We know this as freezing, and going back the other way is melting. And we get solid ice, in this case with water. Any temperature below the freezing point of a substance, that substance will exist as the solid form. And in a solid, the molecules are aligned with each other in a very special way, and what happens is they're fixed. So, for example, this little molecule here is interacting with this, and this, and they're fixed to each other. These are the 3 different phases we're going to talk about: gas, liquid, and solid. And their physical properties are the freezing or melting point. This is the point where liquid water or liquid substance is in equilibrium with solids. So it's the temperature at which freezing or melting happens. And we'll also talk about the boiling or condensing point of water or other substances. This is the point or the temperature in which liquid water or a liquid substance boils or vaporizes to form a gas. And it's also the temperature in which gas forms liquid. So it's the point where the gas and the liquid forms are in equilibrium. I said earlier that if the temperature of a substance is above the boiling point, so if we're, for example, if we're above the boiling point of water, the water will exist as a gas. This is true for every substance. So what substances are gas at room temperature? If a substance is gas at room temperature, that means that the room temperature must be above the boiling point. If room temperature is above the boiling point, then the substance will be a gas. So let's look at this column here, boiling and condensing point. Here, room temperature is above the boiling point for methane, but it's below the boiling point for all of these other substances. And so the only substance in this chart that will exist as a gas at room temperature is methane. Anytime a substance's boiling point is below the temperature that exists, in this case we're talking about room temperature, the substance will exist as a gas. Now let's talk about the solid form, or basically the opposite. If the temperature is below the freezing point of a substance, so we're below this blue line, it will exist as a solid. This is the case for water when the temperature drops below the freezing point of water. This is also true for other substances. Let's talk about the substances that are solid at room temperature. If room temperature were below their freezing point, then the thing would be a solid at room temperature. So if room temperature is below its freezing point, here is room temperature on the column corresponding to freezing point. Room temperature is below the freezing point of these things and above the freezing point of these things. And so when room temperature is below the freezing point, these things will be solid. So these are things that we know exist as solids at room temperature. The most familiar to you might be sodium chloride. This is table salt, and it exists as a solid at room temperature. The things on this chart that are between the two zones we've already highlighted will be liquids at room temperature. So when room temperature is between the boiling point and the freezing point, then those things will be liquid. And water is a very straightforward example of this. The freezing point of water is 0 degrees Celsius, room temperature is 20 degrees Celsius, and the boiling point is 100. So we would have to heat up to make it boil, and we'd have to cool down to make it freeze, and at room temperature it is a liquid. So all of the things in here have a boiling point that's higher than room temperature, so we would have to heat up from room temperature to get them to boil. And they have a freezing point that is lower than room temperature, so we would have to cool down to get them to freeze. But at room temperature, these things are all liquids. Let's practice this concept by labeling the figures on the next page as solids, liquids, gas, or nonsense. On this figure, I've labeled room temperature for you straight across. And on each thermometer, I'm representing a different substance. In the first case, I'm representing a substance whose boiling point and its melting point are higher than room temperature. This would be a solid, because I would have to heat it up from room temperature to get it to melt, so it must be a solid. The same is true for this one. Boiling point is not listed here, perhaps it's too high to measure. But the melting point being higher than room temperature means that at room temperature it is a solid. Here's an example that's similar to water, where the melting point is lower than room temperature and the boiling point is higher than room temperature. Therefore, this substance must be a liquid at room temperature. The fourth thermometer shows a very different situation. This shows a boiling point lower than room temperature and a melting point higher than room temperature. This is actually nonsense. You should always expect the melting point to be a lower temperature than the boiling point. Pause the video here and try to complete the rest of the question before moving on. I'd like to explain what the attractions are briefly. An ionic attraction is a full positive charged ion attracted to a full negative charge ion. For an ionic attraction to be present, you must have a positive ion and a negative ion. These are the ionic compounds that we've talked about earlier in the semester. Another type of attraction is called the dipole-dipole attraction. This only happens with polar molecules. These things are not ions, they are simply polar molecules. Here's a cartoon of two polar molecules, and I'm trying to represent the dipole of the molecule with a partial positive and partial negative end. This is just like the dipole moment arrows that you were drawing for molecules, and in this case you could just represent the partial positive and negative with a dipole moment arrow in the direction of the negative charge. When you have molecules that are polar, the partial positive charge of one molecule will be attracted to the partial negative charge of the other molecule, just like magnets are attracted in the north and south poles. In this case, these are partial charges, whereas in the previous case, they are full charges. The ionic attraction is much stronger than this partial attraction. This is like comparing a very strong magnetic attraction to a weaker magnetic attraction. Another force is called the London force. This is also called van der Waals forces, and these happen between nonpolar molecules. Nonpolar molecules do not have a dipole moment like a polar molecule does. We call the polar molecules permanent dipoles. They will always have a north and a south pole, or a positive and a negative end. In a nonpolar molecule, this does not exist in a permanent sense, but it can be temporarily induced. If one of these molecules has a little bit of a sloshy electron cloud, the electron cloud can temporarily shift to one side of the molecule. This is called an induced dipole, or a temporary dipole. If a temporary dipole happens in one molecule, it will induce a temporary dipole in the other molecule, because the temporary negative end will induce a temporary positive end in one of the other molecules. This is a very weak interaction, and it's much weaker than the dipole-dipole and much, much weaker than the ionic attraction. London forces are the only types of forces that exist in nonpolar molecules, and they're very weak. There's one more type of attraction I'd like to talk about now, called the hydrogen bond. A hydrogen bond is kind of like a special type of dipole-dipole. There are two components that are absolutely required for a hydrogen bond. One is a molecule that contains a hydrogen with a partial positive charge. So this hydrogen has to be bound to an electronegative element like oxygen, nitrogen, or something else. But it has to be part of a polar bond, so this can't be a carbon. The other crucial component is an atom on another molecule that has a lone pair. This atom is typically partially negative, and so the negative and positive charge components of these things are attracted to each other. But it's a little bit stronger than a regular dipole-dipole interaction because these electrons form something close to a bond. This isn't a real regular covalent bond, but it's something very close. It's kind of an almost bond. It's called a hydrogen bond. The two required components are a partially positive hydrogen and an atom with a negative charge. These attractions are listed from the strongest to the weakest. The next thing I'd like to do is focus only on the London forces. The things that only have London forces are down here at the bottom of your chart. Notice that these things are hydrocarbons. They are non-polar molecules. The only attractions in non-polar molecules are London forces, and everything in the following discussion will be pertaining to things like this. If a molecule has stronger forces like dipole-dipole or hydrogen bonding or something else, then the London forces are insignificant because the other stronger forces are more important. So for the next discussion, I'm only talking about the molecules like hydrocarbons that contain only London forces. For these molecules, surface area is the most important factor to determine the London forces. Remember, I'm talking about things that only have London forces. Let's look at two examples. On the first page of your activity, The condensed structural formula and the skeletal structures and the boiling points are listed for hexane and 2,3-dimethylbutane. I'll put the information here. The molecular formula for hexane is C6H14, and dimethylbutane has the same formula. These things are structural isomers. The boiling point of hexane is 69 degrees Celsius, and the boiling point for 2,3-dimethylbutane is 58 degrees Celsius. Notice that hexane has a higher boiling point by 11 degrees. So we'll say approximately 10 degrees higher than the dimethylbutane. Here are the skeletal structures. There's nothing different about these two molecules except for the fact that 2,3-dimethylbutane has branching and hexane is one long chain of carbon atoms. The branching alone can cause this difference in the boiling points, and the reason is because of the surface area. Branching causes less surface area, and it leads to weaker interactions due to London forces. This is very long. It's a long molecule that has lots of surface area, whereas this one is more circular or spherical. A sphere has a much lower surface area than a long tube. And so this molecule over here has less surface area. So it has weaker intermolecular attraction through London forces. This molecule is longer and has more surface area, and therefore they have stronger intermolecular attractions due to London forces. Branching between isomers causes weaker interactions through London forces. It's important to notice, though, that these two things have the same molecular formula, and so we're comparing apples to apples. You would not be able to use this to compare something with a different number of carbon atoms. There's a more important trend when you have a different molecular formula. We saw this earlier in the semester when we first talked about alkanes. This is the chart that you got on an earlier activity on alkanes. And at the time, I asked you to simply notice that when you increase the molecular formula or you increase the number of carbons, you also increase the boiling point. These are all straight chain linear alkanes with no branching. And notice that between each of these, every time I add a carbon, I increase the boiling point almost 30 degrees. Chain length affects the surface area. The longer the chain, the more surface area it has. And notice that because there's a 30-degree difference here, the chain length is more important than the branching between isomers. You should expect that an isomer of hexane will always have a lower boiling point than an isomer of heptane, despite the branching in the isomers. The larger the molecules, the more surface area they have, and the stronger their London forces. Once again, what we just discussed applies only to the things that only have London forces. Surface area is critical for London forces, but it does not tell you anything about the things above this point on the table. If a molecule has a stronger interaction, like dipole-dipole, hydrogen bonding, or something else, the London forces can simply be ignored. Let's look at an example to see how important polarity might be for boiling point. On your activity, I asked you to draw the Lewis structure for methane and chloroform. The boiling points are listed here for you, and they're also on the table on the first page of your activity. Pause the video now and draw the Lewis structures for methane and chloroform. On my slide, I've drawn two Lewis structures of each molecule. I've done this simply to illustrate what the intermolecular attractions really are. In the methane example, I have Lewis structures that have all non-polar bonds. The attractive forces between these two molecules are the intermolecular attractions. Since they are non-polar molecules, the only force here is London. The size of these molecules is essentially the same as the size of these molecules. One major difference is that this chloroform contains a polar bond. I could also represent the polarity of this bond with a dipole moment arrow in the direction of the more electronegative element, chlorine. This is a polar molecule, and the most important attractive force is a dipole-dipole interaction. It's an attraction between the partially negative chlorine atom of one molecule and the partially positive carbon atom of another molecule. The main difference between these two situations is the presence of dipole-dipole interactions in chloroform. Notice the difference in the boiling point is nearly 230 degrees Celsius. This is a drastic increase in the boiling point compared to what we were looking at earlier when only London forces were present. London forces are defined only by surface area, but when there are polar molecules involved, the polarity of the bonds or the polarity of the molecules are drastically more important for the boiling points. More polarity in general means stronger dipole-dipole attractions and a higher boiling point. Please pause the video now and complete this page of the activity. Draw the Lewis structures for water, methanol, and chloroform before you go on. I'd like to talk about part 9C and D. Part 9C asks you to draw the hydrogen bonding interactions of water, and it's the water in the circle. So here's the water in the circle, and I'm going to draw all of its hydrogen bonding interactions. If you want to know how many hydrogen bonding interactions are possible with any molecule, all you need to do is count up the number of lone pairs and add it to the number of partially positive hydrogens. This water molecule has 2 lone pairs and 2 partially positive hydrogens, and so it will be able to participate in 4 hydrogen bonding interactions. I've already drawn one of them for you. The hydrogen bonding interaction should always be written between the lone pair on an atom and the partially positive hydrogen on another molecule. It must be between the lone pair on an atom and the partially positive hydrogen on another molecule. You should never draw a dotted line like this between a hydrogen unless it's partially positive and the atom has a lone pair. Let's draw another hydrogen bonding interaction from this lone pair with a third molecule of water. Here, once again, I've drawn the hydrogen bonding interaction as a dotted line, so it's a partial bond between the lone pair on this oxygen and this partially positive hydrogen. You should be able to draw 2 more. Pause the video now and try it. Here are the 2 other hydrogen bonding interactions that can happen with the water molecule in the circle. Notice in each case, I'm drawing a dotted line between a lone pair and a partially positive hydrogen. A lone pair and a partially positive hydrogen. Water can make 4 hydrogen bonding interactions with other water molecules. And this network expands infinitely in all directions in a glass of water. Now let's try to see what the hydrogen bonding interactions would look like in a methanol molecule. For part 9D, first draw the Lewis structure of methanol and draw its hydrogen bonding interactions. Methanol has 2 lone pairs and only 1 partially positive hydrogen. Therefore, it should only make 3 hydrogen bonding interactions per molecule. Pause the video now and try to draw these. Okay, here's what I would draw. The first hydrogen bonding interaction would be between a lone pair and this partially positive hydrogen on another molecule. Could draw a very similar thing with a third molecule. And in the fourth case, I will draw a hydrogen bonding interaction between my partially positive hydrogen and the lone pair of another molecule. It's very important that you're not drawing hydrogen bonding interactions with the 3 hydrogens that are bound to carbon, because these 3 hydrogens are not partially positive and they cannot hydrogen bond. The difference between these 2 molecules is that the water can make 4 interactions per molecule and the methanol can only make 3 interactions per molecule. This results in a much different boiling point between water and methanol, even though both of these molecules have the same types of intermolecular attractions. Both have London forces, dipole-dipole, and hydrogen bonding. In this case, the hydrogen bonding is the most important and is the strongest interaction, and because water has 4 and methanol only has 3, water has a higher boiling point of 100 degrees Celsius, whereas methanol has a boiling point of 65 degrees Celsius. Stronger attraction, in this case, means more hydrogen bonding, and it means a higher boiling point for water than methanol. Hydrogen bonding can also result in differences in viscosity. Glucose and water can be compared. If you have a solution of glucose dissolved in some water, it looks a lot like honey. So honey is basically sugar dissolved in water. And water itself you are familiar with. Viscosity means resistance to flow, and honey is much more viscous than water. Why is this? Well, count the hydrogen bonding interactions in water and glucose and see if you can figure it out. Thanks for watching this video on attractive forces and physical properties. If you have any questions, please post them in the comments. And if you found this video helpful, please let me know by giving me a vote.